Have you ever considered how pristine a mountain stream truly is, or what unseen particles might be drifting in seemingly clear ocean waters? Beneath the surface, there is a complex world of tiny contaminants that influences water quality globally. The occurrence of microplastics in water is primarily influenced by a combination of key factors including their source, how they are transported, prevailing environmental conditions, the type of polymer they are made from, and their individual particle characteristics like size and shape. Each of these elements plays a critical role in determining where microplastics end up and how abundant they are in various aquatic environments. Understanding the source of microplastics is fundamental. They originate as either primary microplastics, such as the small beads found in personal care products or pre-production plastic pellets, or as secondary microplastics, which result from the fragmentation of larger plastic items like bottles and bags. Human activities are the main driver, with wastewater discharge, agricultural runoff, and industrial processes releasing these particles into ecosystems. Another critical element is how these tiny plastics are transported. Factors such as water currents, wind patterns, and stormwater runoff can carry microplastics over vast distances. The density of the plastic relative to the water is also crucial, with lighter plastics tending to float and denser ones more likely to sink or accumulate in sediments. Environmental conditions significantly impact microplastic fate. Ultraviolet radiation from sunlight, for instance, causes photooxidation which degrades plastics over time, making them more brittle and prone to fragmentation. Water temperature can also accelerate or slow down these degradation processes. Salinity and pH levels influence how microplastics interact with each other and with organic matter, potentially leading to aggregation or disaggregation. Biological activity, such as biofouling where microorganisms from a biofilm on the plastic surface, can alter their buoyancy, causing floating particles to sink and vice versa. The specific polymer type is another major determinant. Common plastics like polyethylene and polypropylene are generally less dense than water and often float, while others like polyethylene terephthalate and polyvinyl chloride are denser and more prone to sinking. Each polymer type also possesses unique chemical resistance and degradation pathways. Finally, the size and shape of the particles are vital. Smaller microplastics can travel further and penetrate deeper into ecosystems, while fibrous shapes from textiles are particularly pervasive due to their widespread use and releases from washing machines. By understanding these intricate influences, we can significantly improve our approaches to water quality management. This knowledge is essential for designing more effective monitoring programs, allowing us to pinpoint areas of concern and measure microplastic concentrations accurately. It also informs the development of targeted mitigation strategies, from improving wastewater treatment to fostering better waste management practices, helping us reduce the influx of new microplastics into aquatic systems. Furthermore, this comprehensive understanding supports the creation of predictive models, which can forecast the distribution and accumulation of microplastics, enabling proactive environmental protection. A fascinating aspect of microplastic science is the concept of the plastosphere, which refers to the distinct microbial communities that colonize microplastic surfaces. These biofilms can alter the microplastic's physical properties, like their buoyancy and aggregation potential, and also influence their role as potential vectors for contaminants. Moreover, the continuous weathering process means that microplastics are not static pollutants but rather an ever-evolving mixture of fragments with changing physical and chemical characteristics. This dynamic nature means that the composition of microplastics in water is constantly shifting. Ultimately, grasping the complex and interconnected factors that govern microplastic occurrence in water is not just an academic exercise. It empowers us to appreciate the true scope of this environmental challenge and guides our efforts toward developing comprehensive and sustainable solutions for protecting our precious aquatic resources and ensuring cleaner water for everyone.
If you love learning about water, like, subscribe, and keep exploring with us.